Welcome to This Explainer. Today, we are tackling something that honestly terrifies a lot of people, but it's actually one of the most beautiful and empowering tools we've got. Imagine trying to describe a breathtaking, complex symphony to someone who's literally never heard music before. Your words can help paint a picture, but eventually, to truly capture the structure and the real magic, you absolutely need musical notation. Well, describing engineering without mathematics? It's exactly the same thing. Math is simply the language that lets us describe, understand, and predict how our physical world actually works.
Okay, let's dive into this, because this is a massive question, and honestly, the anxiety behind it makes total sense. It's something I hear all the time, especially from engineering students returning to grad school after being away for a while. They look at today's complex systems and think, wait, I've forgotten half the calculus I learned years ago. And if modern software can just run all these incredible calculations automatically with the click of a button, do I, as a human engineer, even still need to know the math?
While the answer to that is an absolute, emphatic yes. But here's the secret, and it's probably not for the reason you or a lot of other people might think. If you're imagining that returning to math means endless, tedious memorization or crunching numbers by hand until your fingers cramp up, you can take a huge sigh of relief, because math in modern engineering is not about being a human calculator. No way. It is about something far more profound.
Which brings us to Section 1, the language of engineering.
Think about it like this. Just as English or Spanish lets us communicate complex emotions and ideas, mathematics is just the everyday tool engineers use to communicate physical reality. Take F equals ma. Instead of looking at it as some mysterious jumble of symbols meant to confuse you, think of it as a super concise story. Force produces acceleration. Heavier objects require more force. Boom. In just 3 little letters, Sir Isaac Newton captured one of the fundamental laws of motion. It's a complete narrative. And it's the exact same deal for V equals IR, which tells the story of voltage, current, and resistance, or E equals mc squared, showing the profound equivalence between mass and energy. Learning math is literally just learning a new language. The end goal isn't to push symbols around on a piece of paper, it's to deeply understand what those symbols mean out in the real world.
Moving right along to Section 2, models are not reality. We often grow up thinking of math as exact, perfect, and absolute, but we really need to hit the brakes for a second and totally dismantle that myth. One of the absolute most vital lessons you'll ever learn as an engineer is that a map is not the territory you're walking on, right? A weather forecast on your phone isn't the actual rain falling on your head, and a sophisticated digital twin running on a massive supercomputer is definitely not the actual physical system out in the real world. Why? Because reality is messy. It's infinitely complex, full of friction, chaos, and unpredictable variables. It's way too complex to analyze directly in its pure form. So mathematical equations are just simplified representations of that reality. The famous statistician George Box hit the nail on the head when he said, "All models are wrong, but some are useful." I absolutely love this quote because it completely changes the game on what we're trying to do here. Engineering is not about finding a flawless, 100% perfect mathematical model of reality. Because guess what? That doesn't exist. Engineering is about finding models that are just useful enough to accurately answer the specific questions we care about. Let me give you a really concrete example. Think about studying a satellite in orbit. When we first build a mathematical model for this, we have to make some massive initial assumptions. We assume the Earth is perfectly spherical, we pretend there's zero atmosphere, we ignore solar radiation pressure, and we completely dismiss the gravitational pull of the moon and the sun. Now, are those assumptions actually true? No, of course not. Technically, they're all totally false. But they are absolutely essential. These simplified representations let us strip away all the extra noise so we can actually understand the fundamental core behavior of an orbit. And once we get that down, then we can bring in the more sophisticated models and add all that messy complexity back in.
Let's look at Section 3, Understanding Beats Memorization.
Now, what's really interesting about this slide is that it gets to the absolute heart of the conflict between what we're historically taught to do in school versus what modern machines can actually do today. There's an incredibly clear dividing line here. Think about what your tools do. A calculator multiplies numbers, software solves complex equations, AI generates code. They process blindly, and they do it incredibly fast. But what do you do as the human engineer? Well, you figure out what problem we're actually trying to solve in the first place. You determine if the answer spitting out of the computer makes actual physical sense. You check the units. You analyze how sensitive your result is to uncertainty. Look, memorizing a formula does not teach you how to ask good questions. A computer is going to give you a highly precise number, sure, but only human understanding tells you if that number is actually right. Which leads perfectly into Section 4. Why software needs you.
Make no mistake, we rely on some incredibly powerful automated systems in modern engineering today, but that immense power requires a very steady hand. Just look at the modern toolkit: MATLAB, Python, STK, Simulink, complex CAD software, and highly capable AI assistants. These tools are nothing short of miraculous. They literally save thousands of hours of manual labor. But, and here's the huge warning, they do not eliminate the need for mathematical understanding. Actually, they make it way more critical. Because if you don't understand the underlying math, these programs will happily spin up incredibly detailed, highly impressive, full-color charts and graphs that are fundamentally, dangerously wrong.
Think of it kind of like a commercial airline pilot. Today's autopilot systems are totally remarkable, right? They perform incredibly complex tasks automatically, adjusting thrust and pitch with flawless precision. But that human pilot sitting in the cockpit still has to deeply, fundamentally understand aerodynamics and how that aircraft behaves. Why? So they can intervene when the unexpected happens, like when a sensor completely fails or severe weather comes out of nowhere. It's the exact same for us. Software flies your calculations on autopilot, but you are the pilot. You have to understand those underlying mathematical principles so you can interpret the results, spot the hidden errors, and literally take the controls when the data just does not line up with physical reality.
And finally, Section 5, Building Engineering Intuition. This right here is where we uncover the true, ultimate purpose of studying math. It is absolutely not about passing a test. It's about building mental models of how physical systems behave. So the crucial point is how you visualize these concepts. When you look at a derivative, you shouldn't just see a rigid formula. You should instantly visualize rates of change, like how fast a car is accelerating, or how quickly a water tank is draining. Integrals aren't just arbitrary shapes under a curve. They represent accumulation, gathering up energy or material over a period of time. Differential equations, that's the language of dynamics. Probability is how we wrap our heads around uncertainty and risk. Matrices are just ways to map out complex relationships between a bunch of variables. The equations themselves are really just the hand tools. The real magic is how they physically train your brain to fundamentally perceive the world around you.
I want to let this really sink in for a second. You do not need to remember every single formula. You've got reference books, you've got the internet, and you've got AI for that. But you absolutely 100% do need to understand what the mathematics is trying to tell you. The entire purpose of studying math is to develop your intuition. It's to learn how to reason, how to predict, and ultimately how to make better, safer, and much more innovative engineering decisions.
We are living in an age of incredible artificial intelligence and breathtakingly powerful software. The raw calculations, they're completely covered. But the world does not need humans who just act like slow calculators. The world desperately needs human judgment. So I'm going to leave you with this provocative thought to carry with you. If computers can perfectly calculate the what, will you step up and be the engineer who truly understands the why? Thanks so much for joining me on this explainer. Keep building that intuition, and I will see you next time.